whenever you're ready, Channing, you can start sharing.
Okay, is that sharing the main presentation? Slide.
I can see it.
Excellent.
One more can confirm. Perfect. Yeah, take it away.
Cool. Yeah, thanks, Demetrios. Thanks for the intro, and hi, everyone. So I'm Channing Syms. As Demetrios said, I'm the Fish Passage Design Manager for WSDOT right now. This presentation is a kind of accumulation of my research that I did at the University of Idaho, and keying in on Pacific lamprey. They're an odd creature and they're very different. It was a lot of fun. It was a lot different than what we focus on. They aren't commercial, so there's not as much funding, and people don't focus as much on lamprey as they do salmon, like in this area. But yeah, my paper is titled "A Biologically Based Measure of Turbulence Intensity for Predicting Fish Passage Behavior." My co-authors were Mark Kurt, Chris Cotto, and Daniele Tonina with the University of Idaho. Our paper was published in 2021. Okay, so kind of to give you guys an idea of the issues here, the vertical slot fishways that we normally see kind of in most of the dams, and a lot of fishways are designed after what was done at like Bonneville, John Day, and all of the other dams on the Columbia Snake River system. They're designed for salmon and no other species who were really looked at for those designs. For instance, lamprey passage in what we call the Serpentine Weirs, and we'll see a picture in a minute of what those look like, is only 25 to 30%. So only 1 out of 4 fish that make it to the lower end of that fishway make it up to the top. They either turn around and go find another place to spawn below the dam, or they just don't make it. And there's a lot of predation by sea lions and seals of the lamprey. They taste like butter. It's just like eating a stick of butter is kind of the way you can look at it. So we designed a flume to represent exactly what the fish are seeing in these fishways. So turbulence, velocity, and a slot length that you normally see in those concrete fishways. And just kind of give you an idea of where we are. So here's Bonneville Dam. It's about 40 miles upstream on the Columbia from the mouth. And you can see this is in the center. There's an island that's called, I lost the name of the island, but anyway, they're one of the Bradford Island, and this fishway is the one that comes up, and it's got the Serpentine Weirs within it. So if you think about it, fish swim in different ways, and every fish is a little bit different. Salmonids and most of the fish that we think of as commercial fish are subcorrigivore swimmers, so they use the tail to do most of their propulsion. Whereas like a lamprey is an anguilliform swimmer, so they're more like a snake, you could say, and they kind of slither through the water. Pacific lamprey actually have an additional bonus feature, you could say. They have a saltation ability, so they can actually attach to smooth, flat surfaces and do a little burst and jump. And I have a really cool video of them doing that later. But at about 1.8 meters per second, they kind of switch their swim motion from this anguilliform style to that burst attached swimming. And we found that they can only do that for so long before they just give up. They just can't do it anymore. Like I said earlier, Bonneville Dam is here, about 43 miles from the mouth of the river, just upstream from Portland. And our fishway is located on Bradford Island in the center of the Columbia River here. And if you see where it says AFF, that's our actual flume where we did our test at. So we used the same water and everything that's coming into the fishway. There shouldn't be any difference. And just to do a test, and here you can see these are the serpentines that occur for the fish to get up. Okay, so Serpentine Weirs. Bonneville was one of the first to include these structures. They work really well. As I said earlier, for some audits, they create that kind of lower flow area with resting pools. You can see the pools here, they're more for the resting. And then some audits can burst through these slots, and they navigate them really well, and it's a lot like nature. It's how salmon navigate through nature. They use those rocks and the flumes that we see, sort of like our structures that we design today. So we set up our flume to have a total of 9 different treatments. So we have both here, you have slots. These are the slot lengths here, 0.33 meters. This is the first treatment. Then you have a control, which is just bursting through a slot. And then we have a separate one that creates turbulence here. And that wall it creates an eddy, just like you see in the serpentine fishways. And then we have 3 different velocities that we ran through. So a bulk average velocity of 2.4, 1.8, and 1.2 meters per second. And then, we added a longer length, so we made that slot a little bit longer to see if that affected how the lamprey swam through. And then finally, we made it almost a full meter long. And we did both. We ran fish through as part of our partnership with the biology group, and then we also did our hydraulic tests through the system. So we developed a robot here with a micro ADV, and we measured velocities at 3 different elevations, and it also measured turbulence at those 3 elevations too. So each measurement was 4,000 samples, and we took 33 measurements at each elevation of 0 centimeters from the bottom to 30 centimeters from the bottom and 65 centimeters from the bottom. And we just measured all of those through there. So this is what the data comes back as. So this graph here, as you can see, these are 4,000 samples. And then and it measures velocity in all 3 directions. So in Z, the U, and the V direction. So we calculated average velocity, vector average velocity. So that's in all 3 directions together. Standard deviation, which is basically turbulence. Intensity, so you divide it by the velocity, which gives you a different measure of turbulence. And then finally, turbulent kinetic energy, which is basically the vector averaged of the turbulence instead of the velocity. And then, just to show you kind of what that average velocity that's used to measure intensity is, that's what that is. Okay, and this is our measurements in the flume. You can see how this eddy is created here. And this is the robot going across doing measurements there. Yeah, so now this next video, it's actually used in the flume to kind of show what was going on and basically what the lamprey are seeing underwater at that 0 centimeter mark. And this will be, you can see this arrow here, the GoPro will actually be coming out and then going around, which is what we actually saw a lot of the lamprey doing during their test. You can see how much turbulence there is there and what the fish actually have to navigate getting through these flumes. Cool, so I can pause there for a quick second, see if there's any questions. I don't see any here. Okay. All right, so now velocity results. So these, if you look down here at the bottom, we had different lengths. So 1 weir, 2 weirs, and 3 weirs. And then you have high flow, medium flow, low flow. And then you can see the variations in the velocity. And this is kind of just our little error bars here on how much variation you have. And variation of velocity equals turbulence. So how turbulent is that flow and what do we have to deal with? And then you can see that there's slightly more variation in the velocity in the turbulence treatments here. So these, if you remember back, we have the control and then the turbulence. So the turbulence is the wall. But now if we go, now this is the turbulent kinetic energy. And this is where you see the big difference. You can see in those turbulence treatments, that variation is much, much greater than in the control. And it's much lower as far as turbulence in the control as well versus this. And now these are 3D contour plots of different components within here. And then we're going to have, I'll show you different ones at different levels. So if you look up here, you have your different elevations. So these are all going to be at 0 centimeters. We saw most of the lamprey, they actually stuck to the bottom. The way they swim, they use their saltation on the bottom of the flume to kind of get through and navigate. So yeah, you can see these areas of different velocities through here, and U component is screen-wise, or bulk velocity is U, so left, right in your screen. And then this is the turbulence treatment. So if we go back, you can see how much more consistent the velocities are through here. So the fish could find swim paths, where here you have these really high velocity areas and differentiation. So the fish really have a hard time finding a path that's easy to get through there. Because if you think about it, the 1.8 meters per second is much lower than what most salmonids can swim. And they just, the lamprey can't do as well.
Channing,
yes.
Can I ask a question here?
Sure.
So the colors here represent velocity gradients you were talking about. And what do the two axes mean?
So here you have well, this is just a plot of the actual flume. So it's a contour plot of the flume. So this is the 1 weir sticking out. These are 2 weirs, and this is 3. So this is a contour plot of all of the measurements that we took throughout the flume.
Okay, so we're not talking about inches. It's much smaller in size, right?
These are centimeters.
Centimeters, okay.
Yes.
So it is pretty long. So.
Yep. So we have basically 1,000 centimeters here. So, and then 800 wide.
Okay, perfect. Thank you.
Okay, and then V component. So this is velocities in the up-down direction. There's much less variation here, which is reasonable because our bulk velocity is left-right. You can see a little bit more in control, especially around the front ends of the walls, because if we have, so in each of these, your turbulence wall is approximately here. So it actually creates that eddy right there on each one. And then, so the key here to think about the lamprey, when they attach to the bottom, that upwelling motion will actually pull them off. And if they lose that section onto the bottom, they basically get blasted back downstream. And if you look here in the turbulence treatment, that's pretty high. And now we can look at velocity. So those are all, these are average. This is the average velocity, so all 3 directions. So you can see here again, these are pretty high in this one. That makes, and then if you go over, there's much higher velocity in these turbulence treatments. The average velocity is always going to be the same, but you have these higher velocity areas due to that turbulence wall. And now the turbulence. So if we look at this one, you can just see that without that wall, you have hardly any turbulence through these. There's a little bit here, and that's probably, we think that was just due to the kind of harmonics that happen with medium discharge versus, and the one weir, there's something that created a harmonic there. It created a higher turbulence, and we actually saw that when we were viewing and when we were observing. And then if you switch to the turbulence wall, you have a lot more turbulence in here, and these fish really struggled with these. So now, with that data and just analyzing these contour maps, we developed an algorithm and actually made a program to solve what is the easy path for fish to swim. So this dark black line you see here, that is the algorithm calculated easy path for the fish to swim through based on TKE and also based on velocity. These other lines through here are actual swim paths of lamprey. So we mapped out those swim paths, and you can see, especially in this one, that the fish tended to swim what we calculated as the easy path. In the control treatment, it was less obvious because there were multiple easy paths. Like for instance, this one, the easy path is here, but it's not much different up here. And then once you add that turbulence wall, it seems to be much more obvious. The fish really do swim where that, like especially in the TKE, they kind of followed exactly what the calculated path would be through there, because it's easier. So now you can see this is the control. So this is 2 weirs with medium velocity. And we're going to see how the lamprey swims. Now, this is the same thing. Now,
Channing, just want to bring to your attention that, at least for me, while the video was playing, we could not hear you. I could see that you were talking, but we could only hear the video.
Okay. Yep. So the first video, it was just a control treatment, and I can go show them again in a second. And it's 2 weirs with medium velocity. And it was just to show how fast the fish swam through. In the second video, you could see that he attached and he didn't move, and that was with that turbulence wall with 2 weirs and medium velocity. So you can see that they, instead of blasting through there, he actually had to attach. He does end up getting through, but he attaches for quite a bit longer. Well, at all. In the first one, he actually doesn't attach. And you see him just kind of blast through there. You should be able to, can you hear me now? Okay. And then with the turbulence, he attaches. So with that, we actually did quite a bit of literature research to try to figure out, okay, so we see that it's pretty obvious that turbulence makes a huge difference on how the lamprey move through the system. And it appears that with high turbulence, we also have a lot more attachment time. So we did a literature review to try to figure out, has anybody looked at the turbulence and how that affects fish and how it affects passage through fishways. And there's a little bit out there, but not a whole lot. Because mostly it's driven by velocity. Almost all fishway design is velocity depth, and that's it, unless you have kind of drops and you need that dissipation energy through there, but it's mostly velocity and depth. So there's a little bit of research we found was a power equation, and then there's a work equation. So we've run both of these. The power equation uses the drag coefficient of the fish, the surface area, and then how far he travels, and then how much time to pass through the slot. So we evaluated that, as well as looking at that turbulence and how much work would be required. So you basically take the sum of the velocity and the square root of the turbulent kinetic energy through the slot in order to find out how much work would be required to travel through there. So when we compared that work equation and we did a similar contour plot, you can see that it's similar to what TKE showed earlier, but it gives a little bit better path following from earlier. And then once you look at it in the turbulence treatment, I think this one follows perfectly, these follow perfectly, and some of the variations just have to do with fish behavior. Fish aren't always going to follow exactly the same thing. So then when we looked at the correlation and look at this deviation here and the R squared, and those values really weren't very good. I mean, there's so much variation in here. And then the same for, so this is power, and then work. You have a little bit better of an R squared value, but I can't say that this is a good equation to use to solve that. So we stepped back and said, okay, well, this doesn't really work. What makes sense here? So we developed a different equation using kind of a biological intensity. So we took the square root of TKE and divided it by what we considered the behavioral changing velocity, which in this case is 1.8 meters per second, because that's when lamprey changed their behavior. And you could do the same thing for like salmon. I think, 4 feet per second is when they change to a burst instead of just a swim behavior. So you could use similar attributes to different fishes in order to determine, okay, where is that behavior changing and what does that provide a good value to solve for designing fishways for all different life. And then we also, on top of that, created a separate equation using just kind of the same thing as above, but we multiplied it by this U star values. That's, again, the bulk velocity divided by this biological changing velocity again. And then when we run that, so this is the first equation, the iBio. So we get much closer. We had an R squared of 0.35 here. And when we break it out by control and turbulence, instead of doing it all as one bulk, we actually got a little bit better of 0.4 and 0.5. And then, so for our F value, it got even closer. So we got 0.56 for everything. So we found that it was pretty good. And so our kind of conclusion was that we should make sure that, well, we'd like more tests to see if our equation was good and if it would work for other species. This was very focused on lamprey because lamprey are difficult. No one's studying them, so we didn't know what kind of velocities lamprey, or what kind of fishways, what was failing in these serpentine weirs, basically. Why can't lamprey make it through them? We found that was turbulence, but how do you design a fishway to meet those turbulence requirements, and what do you do to move forward? This equation could be a good solution for that, but it does require more studies and more tests. The one thing we did find is turbulence does appear to be a really good predictor of whether or not lamprey are going to make it. They don't seem to mind velocity. It doesn't really affect them. They switch to their burst motion, and as long as there's nothing lifting them off the bottom, they just make it. They're good. So kind of part of our projects that we did, so this is on Bonneville Dam. So how do you create lamprey passage? The Serpentine Weirs in this are around the corner. This is kind of the bulk fishway where all the fish come in and then they swim around. So we designed these aluminum flumes for the lamprey to make it up. And so this is John Day Dam here. We designed one here. It's located on this facility. And there's one over here as well to get lamprey up and above John Day Dam. And this is the design that I did for that one. So you have the entrance here. They swim up the flume, and at about 30 feet of elevation, they need a rest box to sit, and then they sit there, they go in there and rest. These boxes fill up, and then they move up here, and they put them in a trap box, and then that trap box gets elevated up over the dam, and then they get dumped on the other side. So yeah, they're just really they're sheet metal aluminum that's just folded into place and then bolted together with flanges, and then we use silicone each flange together so you have a smooth transition between the different surfaces. I know it's 25 feet, not 30. And this is what we call an upwelling box. So does the lamprey get put in here, and then they'll swim out into the trap. So yeah, this is on John Day Dam, and we were able to get in there and actually construct these while the fishway was completely dry. Yeah, and these bollards here to guide the lamprey into it, they seem to follow these pathways, and they'll get in and swim up. And this is setting the palms. Yeah, and another thing that the Corps is trying, and it seems to work okay, is so in these types, the spillover fishways, the weirs, they actually cut holes in the bottom, and the lamprey seem to find those holes to swim up. They seem to be confused by the weirs, so they don't actually seem to like to go over them. But with these orifices here, they make it through better. It's not perfect, but it's better. So yeah, in this video here, this one's kind of cool. This is a completely vertical face with only a laminar sheet of flow over top of it, and the lamprey can actually make it up. So you see, this is their saltation. They stick to the side, and I don't know if you guys have ever seen, they do the same thing at Willamette Falls in Oregon. The lamprey will actually climb up the waterfalls, and you see him just kind of jumping up. And he makes it right over, and that's a completely vertical face with an aluminum sheet behind it.
This is incredible, I have to say.
They're a very weird creature that I kind of fell in love with through these projects. So they're very interesting, and yeah, and it just shows you that our focus on commercial fisheries isn't always the best ecologically. Lamprey appear to be an important piece of the ecosystem. I mean, the amicites are eaten by salmon, and all of the marine mammals love those things. They're like I said, they're a stick of butter. But yeah, with that, if you guys have any questions, I'll open it up.
Well, thank you very much, Channing, for the incredibly interesting presentation. Does anybody have any questions for Channing?
Yeah, I have one, and again, it's really fascinating, and clearly I have little familiarity with the Lamprey and all that's being done. But one of the things you had mentioned, Channing, is that relative to the turbulence and their ability to, get over or climb up through these flumes and such. Did you look at the time and you showed some graphs about the time and the distance, but how did that play into their success rate? When you had this obstacle, this turbulence, high velocity, and if you shorten the distance between resting areas, did that make the success a lot higher?
Shorting the distance between resting areas, it does appear that it's accumulation of work. So if they are having to work for a longer period of time, they fail more often. And it does apply to their attachment time too. So if we looked at how long they attached for, that seemed to correlate with how much turbulence there was. But yeah, you're getting back to like how many resting areas they have and how much time it takes to get through for total work. Yeah, we looked at that a little bit, but with our limitations on the flume length, it was a little more challenging to actually make that kind of experiment work. But those studies have been done, and that's how the 25 feet was developed. So Mary Moser with NOAA actually did a study on how much work it requires to get through there, and that's why she decided at 25 feet on the height of the fishway was all they could do before they started having troubles.
Thanks.
We do have a question from Tom Hardy. Do different species of lamprey behave similarly at fish passage structures?
No, Pacific lamprey are different in that they have the oral disc on their bottom. So when they moved to the salt water, they actually changed to parasitic creatures, and they actually developed that disc on the bottom, and they can attach. So they have that saltatory motion. Other lamprey are more like eels, so they never developed that disc to be able to attach to things. So yeah, and they struggle a lot more, especially in high velocity environments.
I see. Anybody have any other questions?
Yeah, Robert?
Robert, yeah.
I think you kind of answered the question there, but I'm originally from the Cleveland area, and Great Lakes are I think constantly battling these with the electric fences. Is that correct?
Yeah, they do all kinds of things. We actually use some of their research on how they keep them out to figure out how to keep them in. We were using some of the reverse research because they're struggling with keeping the lamprey out of things, and they're very invasive and they're very bad in the Great Lakes. So yeah, we did use some of their research to reverse ours.
Nice. That's what it was going to be. Is any lessons learned from that battle? Because I mean, how they came in from ballasts? Is that correct?
Well, the canal too.
The canal, and made their way through.
Yeah.
So that's pretty cool. You've been able to use some of their work over the years.
Yeah, it was kind of interesting because I actually went to a couple of seminars and conferences where the Great Lakes people would come up to us and say, why are you trying to save these things? They're bad. But yeah, and they were fine. It was just fun. It's interesting though how different creatures are different in different places.
Mm-hmm. Is it a similar species?
They're similar. Not quite the same, but similar.
Cool. Thank you.
Yeah.
Cool indeed. Anybody else? Any questions? Well, I did have a question for you, even though I think you kind of answered it. You know, I was amazed to see that steep incline with the aluminum flutes that you had, the passageways that you had. I mean, I was thinking that, you know, the water velocity alone going down, how would they go against that? But you said that they attach, so it's irrelevant to them, the water flow velocity. Why can't they apply the same propulsion technique even at the high turbulence areas, you know, across the stream? Because they cannot attach.
Yeah, the turbulence really, that upwelling motion, it pulls them off and they can't use their saltatory motion, that suction. Whereas if it's a laminar flow, like we have in those aluminum flumes, like even a vertical one, because there wasn't turbulence there to push them off, they can attach and move through. It's really interesting how they use that saltatory motion.
Yeah, amazing.
And that's what they do in the ocean. They attach to fish, larger fish, the same way. They don't swim very much once they hit the ocean. They kind of find a host and travel with them.
Yeah. One more question that I did have also, it was from the beginning of your talk. You mentioned that the passageways were, of course, for salmon, but so the lampreys were not considered at all because?
Commercial fisheries. Lamprey are not a commercial fish. That's kind of the result of that.
I see. Okay. Any other questions from anyone? Okay. Well, if nobody has any other questions, I'm going to give you 15 minutes of your time back. And thank you again, Channing, for the incredibly interesting presentation. I learned a lot of things that I had no knowledge of, actually.
Absolutely.
But you presented it in a scientific way as well, so it was doubly engaging, let's say.
Yeah, thanks for the invite. And yeah, if anybody has any questions or anything like that, they can reach out. So
yeah, feel free to reach out directly to Channing or even to me, and I will forward your questions to Channing. Okay.
Thank you.
Thank you very much, everybody.
Bye.
Take care. Have a nice evening.
Oh, is there a question?
Was there a question? Sorry. No, I didn't. No, not another question. Take care, Channing. Thank you.
Bye.